Look up at the night sky. What do you see? A tapestry of stars, distant galaxies, the shimmering glow of cosmic wonders. But here's the startling truth. Everything visible to our eyes, every star, every planet, every speck of light, makes up less than 5% of the universe. The rest, an invisible, enigmatic force known as dark matter, silently weaving the fabric of reality itself. It's the unseen hand guiding galaxies into their majestic spirals, the ghostly scaffold holding the cosmos together. And yet, despite its overwhelming presence, dark matter remains one of the greatest unsolved mysteries in science, a shadowy puzzle that has eluded detection for decades. Think about that for a moment. We live in a universe where the majority of its mass is completely invisible to us, detectable only by the faintest gravitational whispers it leaves behind. Like a master architect working behind the scenes, dark matter shapes the grand structures of the cosmos without ever revealing itself. Without it, galaxies would fly apart, cosmic webs would unravel, and the universe as we know it would cease to exist. So how do we begin to map something we can't even see? How do we trace the footsteps of an entity that refuses to interact with light, with matter, with anything except gravity? That's the journey we're embarking on today, a voyage into the unknown where cutting-edge science meets the edges of human imagination. From the eerie gravitational fingerprints dark matter leaves on distant starlight to the mind-bending experiments deep underground searching for its elusive particles, we'll uncover the ingenious ways scientists are piecing together this cosmic puzzle. This isn't just a story about astronomy, it's a detective story, a quest to decode the hidden blueprint of the universe itself. And by the end, you'll see the night sky and our place within it, in a way you never have before. The trail of dark matter is faint, but it's there, and we're following it. Imagine holding a snow globe, shake it, and the glitter swirls around, tracing invisible currents in the water. Dark matter is like that glitter, revealing itself only through the way it moves everything else. We can't touch it, see it, or even detect it directly, yet its presence is written into the very fabric of space. When astronomers first noticed stars orbiting galaxies faster than expected, or light bending around seemingly empty patches of sky, they realized something extraordinary. The universe is filled with a hidden substance, one that tugs on the visible world like a puppeteer pulling strings. The most baffling part, dark matter doesn't behave like ordinary matter. It doesn't clump into planets or stars, doesn't collide with atoms, doesn't even cast a shadow. It's a cosmic ghost drifting through walls, through planets, through us without a trace. Yet its gravity is so powerful that entire galaxies are embedded in vast halos of it, like pearls suspended in invisible silk. Without these halos, galaxies would spin apart, their stars flung into the void like marbles rolling off a table. So what could this mysterious substance be? Some scientists think dark matter might be made of WIMP hypothetical particles heavy enough to explain its gravitational grip, but so shy they barely interact with normal matter. Others propose actions, particles so lightweight they flicker in and out of existence. Then there are stranger ideas. Could dark matter be primordial black holes forged in the chaos of the Big Bang? Or something even more exotic beyond our current theories? Every experiment from deep underground detectors to telescopes mapping the distortion of starlight is a hunt for clues. This isn't just about identifying a missing ingredient, it's about rewriting the rules of reality. If dark matter is a particle, it would mean the universe contains an entire hidden physics, a secret layer of existence humming just beyond our perception. And if it's something else entirely that could unravel the very foundations of Einstein's gravity, the stakes couldn't be higher, because dark matter isn't just out there, it's the reason we're here at all, the silent architect of every galaxy, every star, every planet. And its secrets are waiting to be found. The story of dark matter begins not with a eureka, a moment, but with a nagging inconsistency, one that would unravel our understanding of the cosmos. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a sprawling collection of galaxies millions of light years away. He noticed something bizarre. The galaxies were moving far too quickly to be held together by the gravity of visible stars and gas alone. By his calculations, there simply wasn't enough mass to keep them from flying apart. Zwicky called this missing mass Dunkelmaterei, dark matter, a term that would echo through history, even as his colleagues dismissed the idea as too radical. But science has a way of circling back to the truth. Decades later, astronomer Vera Rubin picked up the trail, armed with more precise measurements and an unshakable curiosity. She focused on the rotation of spiral galaxies, expecting stars at the edges to orbit more slowly, like planets farther from the Sun. Instead, she found stars whizzing around at nearly the same speed regardless of distance, as if some invisible anchor were holding them in place. The math was undeniable. Galaxies contained 6 times more mass than could be seen. Rubin's meticulous work turned Zwicky's fringe theory into a cornerstone of modern astrophysics, proving the universe was filled with something we couldn't see, touch, or explain. What's remarkable about these discoveries isn't just the science, it's the human perseverance behind them. Zwicky, a brash and brilliant outsider, faced skepticism for years. Rubin, a woman in a male-dominated field, had to fight for telescope time and recognition, yet their stubborn pursuit of the truth reshaped cosmology. They showed us that the universe plays by hidden rules, and that the most profound revelations often come from questioning the gaps in our knowledge. Today, we stand on their shoulders, peering deeper into the dark. We've mapped the cosmic web, vast filaments of dark matter stretching across billions of light years, guiding galaxies into their celestial dance. We've watched light bend around invisible masses, a phenomenon called gravitational lensing, as if space itself were a funhouse mirror warped by unseen hands. Every clue points to the same conclusion: dark matter isn't just a small piece of the puzzle. It's the framework, the scaffolding, the hidden architecture of everything. And yet, after nearly a century of searching, we still don't know what it is. That's the thrilling paradox at the heart of this mystery. The more we learn, the more we realize how much remains just beyond our grasp. Gravity doesn't just pull, it bends. Picture a beam of light traveling for billions of years from a distant galaxy, only to have its path twisted by an invisible hand before it reaches our telescopes. This eerie phenomenon, called gravitational lensing, is dark matter's signature. Just as a magnifying glass distorts the words on a page, vast clusters of dark matter warp the fabric of space itself, bending light like a funhouse mirror. And it's not subtle. Some of these cosmic mirages stretch galaxies into surreal arcs or even duplicate them, creating ghostly multiple images of the same celestial object. Einstein's theory of relativity predicted this effect over a century ago, but even he might have been astonished by how it's used today. By analyzing these distorted images, astronomers can trace the unseen mass responsible for the warping, like detectives studying fingerprints at a crime scene. The most stunning part, these lenses aren't made of stars or gas, they're crafted by dark matter's gravity alone. In places like the Bullet Cluster, where 2 galaxy groups collided, scientists witnessed something extraordinary. visible gas slowed and clumped from the impact, while the dark matter, unfazed, sailed straight through, leaving its gravitational imprint on the light behind it. The result, a perfect separation between the seen and the unseen, proving dark matter's existence beyond doubt. But gravitational lensing isn't just proof, it's a tool. By mapping these distortions across the sky, researchers have reconstructed sprawling three-dimensional charts of dark matter's distribution, revealing a hidden cosmic web. Filaments of invisible matter stretch across unimaginable distances, connecting galaxies like beads on a string. Some of these dark matter highways are so massive they warp the light of thousands of background galaxies at once, creating intricate patterns that supercomputers decode into maps of the invisible universe. Here's where it gets even stranger. Sometimes the lensing effect is too subtle to see directly, but statistics reveal its presence. By measuring tiny, systematic distortions in millions of galaxies, a technique called weak lensing, scientists can detect the faintest gravitational whispers of dark matter, even where no single lens stands out. It's like listening for a whisper in a crowded room by analyzing the rustle of every leaf in the forest. What's remarkable is how much this silent architect shapes our view of the cosmos. Without dark matter's lensing effects, some of the universe's most distant galaxies would remain hidden, their light too faint to reach us. Instead, dark matter acts as a natural telescope, magnifying and revealing objects we'd otherwise never see. It's as if the universe itself is helping us peer deeper into its secrets, using its own hidden structure as a guide. And with every new lens discovered, we're not just finding dark matter, we're rewriting the story of how the cosmos builds itself. Consider the birth of a galaxy, a process so delicate, so precise that without dark matter, it would be like trying to build a skyscraper in a hurricane. In the chaotic aftermath of the Big Bang, ordinary matter, the stuff of stars, planets, and us, was far too scattered and energetic to coalesce on its own. Atoms zipped through space at incredible speeds, repelled by heat and radiation like leaves caught in a storm. But dark matter, unaffected by light or pressure, moved slowly, steadily, its gravity acting like a cosmic glue. Wherever dark matter pooled, it created gravitational wells so deep that gas and dust had no choice but to follow, collapsing into dense pockets that would eventually ignite into the first stars. This wasn't a quick process. Over hundreds of millions of years, dark matter's invisible tendrils wove through the universe, drawing matter into vast filaments and knots. Computer simulations reveal something astonishing. If you remove dark matter from these models, the universe remains a featureless sea of gas. But add it back in, and suddenly, galaxies emerge, spirals with their graceful arms, ellipticals like glowing orbs, even the irregular dwarfs clinging to their larger siblings. Dark matter didn't just assist in galaxy formation, it orchestrated it. Without its gravitational blueprint, the universe would lack structure, a canvas without brushstrokes. Take the Milky Way as an example. Our galaxy is embedded in a halo of dark matter so massive it outweighs all its stars by a factor of 10. This halo isn't static, it's dynamic, a living framework that continues to shape our cosmic home. When smaller galaxies drift too close, the halo's gravity tears them apart, their stars strewn into streams that wrap around the Milky Way like celestial ribbons. Even now, dark matter's pull is drawing the Andromeda galaxy toward us, setting the stage for a colossal merger billions of years in the future. But here's the twist: dark matter doesn't just build galaxies, it preserves them. Stars orbiting a galaxy's edge should, by all rights, slow down as they move farther from the center, like planets in our solar system. Instead, they race along at nearly the same speed, held fast by the invisible grip of dark matter. Without it, galaxies would spin themselves apart, their stars flung into the void. This delicate balance between motion and gravity, between chaos and order, is dark matter's silent masterpiece. And the story doesn't end there. Dark matter's influence extends to the largest scales imaginable. Galaxies don't float alone. They cluster into groups, superclusters, and filaments that span hundreds of millions of light years. These structures trace the contours of the cosmic web, a network of dark matter so vast it dictates the flow of the universe itself. Where filaments intersect, galaxies gather like cities at crossroads, their fates entwined by the unseen threads of dark matter's design. Yet for all its power, dark matter remains elusive, a ghost in the cosmic machine. We see its handiwork in the rotation of galaxies, the bending of light, the grand architecture of the universe, but we still don't know what it is. That's the haunting beauty of this mystery. The very force that shaped our existence refuses to reveal its nature. Every galaxy, every star, every planet carries its signature, a reminder that the universe is far stranger, far richer than we ever imagined. If dark matter is the universe's invisible architect, then dark energy is its rebellious counterpart, a force so strange it defies gravity itself. Picture a cosmic tug-of-war. On one side, dark matter's relentless pull, weaving galaxies into existence. On the other, dark energy, an enigmatic pressure stretching space apart, accelerating the universe's expansion like an unstoppable tide. Together, they dominate the cosmos, making up 95% of everything that exists, yet we've barely begun to understand their dance. The discovery of dark energy was as unexpected as it was revolutionary. In the late 1990s, astronomers studying distant supernova made a startling observation. The universe wasn't just expanding, it was accelerating. This flew in the face of everything we knew. Gravity should have been slowing the expansion, pulling galaxies back like a rubber band snapping taut. Instead, something was overpowering gravity, pushing galaxies apart faster and faster. That something we now call dark energy, a mysterious influence embedded in the fabric of space itself. Here's where it gets even stranger. Dark energy isn't just a force, it's a property of empty space. According to Einstein's theory, empty space isn't truly empty, it crackles with energy. Normally, this energy is negligible, but as the universe expands, more space is created, and with it, more dark energy. The result, a runaway effect where the push of dark energy grows stronger as the cosmos grows larger, like a snowball rolling downhill, gathering speed indefinitely. But dark energy doesn't act alone. Its cosmic rival, dark matter, works tirelessly to hold the universe together. While dark energy stretches the space between galaxy clusters, dark matter's gravity binds galaxies into clusters and superclusters, creating vast cosmic cities that resist the expansion. This tension between the two shapes the fate of everything. If dark energy dominates, the universe will expand forever, growing colder and emptier until galaxies are isolated islands in an ever-darkening void. If dark matter's gravity gains the upper hand, the expansion could reverse, collapsing the cosmos in a fiery, big crunch. And in the most extreme scenario, dark energy might grow so strong it tears apart galaxies, stars, even atoms themselves, a fate called the Big Rip. What's fascinating is how little we know about either force. Dark energy could be a constant, unchanging presence, or it might evolve over time, its strength waxing or waning. Some theories suggest it's tied to a mysterious field called quintessence, while others propose it's a sign that Einstein's gravity needs rewriting. Similarly, dark matter's true nature remains just out of reach, with experiments worldwide hunting for even a whisper of interaction. This isn't just academic curiosity, it's a quest to understand the ultimate destiny of the cosmos. Every observation, from the bending of light around galaxy clusters to the precise mapping of the universe's expansion, brings us closer to answers. The interplay between dark matter and dark energy is the great story of our universe, a tale of creation and destruction written in the invisible ink of physics. And as we peer deeper into the darkness, we're not just uncovering the secrets of the cosmos, we're learning how the story ends. Deep beneath the Earth's surface, in abandoned mines and mountain tunnels, scientists have built some of the most sensitive detectors ever conceived, not to find gold or rare minerals, but to catch a ghost. These cavernous laboratories, shielded from the constant barrage of cosmic rays and radioactive noise that bombard the surface, are hunting grounds for dark matter. Imagine a vat of liquid xenon, chilled to nearly -100 degrees Celsius, waiting in utter darkness for the faintest flicker of light or the tiniest electrical pulse, a sign that a dark matter particle has, for once, brushed against an atom of ordinary matter. That's the heart of experiments like LUX Zeppelin and Xenon 1T, where even the slightest vibration could drown out the signal. Teams monitor these detectors around the clock, knowing the odds are staggeringly low. A dark matter particle might interact with their setup once a year, if at all. The sheer scale of these experiments is mind-bending. The LUX Zeppelin detector, for instance, holds 10 metric tons of liquid xenon in a tank so pristine it makes a surgical suite look dusty. Surrounding it are layers of shielding water, copper, even ancient lead mined from Roman shipwrecks, chosen because its low radioactivity won't interfere with the hunt. It's like trying to hear a whisper in a hurricane while standing inside a soundproof room. And yet, despite this painstaking setup, dark matter remains stubbornly silent. But silence itself is a clue. Every time these detectors come up empty, they rule out another swath of possible particles, tightening the noose around the mystery. Meanwhile, halfway across the world, another approach is underway. Beneath the border of France and Switzerland, the Large Hadron Collider, the world's most powerful particle accelerator, is smashing protons together at nearly the speed of light, recreating conditions that existed just moments after the Big Bang. The goal: to manufacture dark matter on Earth. When these particles collide, they release energy that can briefly coalesce into new forms of matter, some of which might include the elusive particles scientists are chasing. The trick is that dark matter, by its very nature, wouldn't register in the collider's detectors. Instead, researchers look for imbalances in energy, moments when particles seem to vanish, carrying momentum into the unseen realm of dark matter. It's a bit like trying to deduce the presence of a thief by noticing missing items in a locked room. So far, the collider hasn't spotted any definitive dark matter signatures, but it has chipped away at the possibilities, narrowing the field. Some theories, like supersymmetry, which predicts a whole family of yet undiscovered particles, are hanging by threads, their credibility fading with each null result. Others, like the idea of dark matter as a hidden valley of particles that barely interact with ours, are gaining traction. The longer the search goes on, the more creative scientists must become, venturing into theoretical landscapes that once seemed like science fiction. What's remarkable is how these two approaches, underground detectors and particle colliders, complement each other. One listens for dark matter's whisper in the quietest places on Earth. The other tries to shout it into existence through brute force. And there's a third frontier, the sky itself. Telescopes like the Fermi Gamma Ray Space Telescope scan the heavens for indirect clues, like gamma rays that could be the fallout of dark matter particles colliding and annihilating in space. Others monitor neutron stars, whose incredibly dense cores might capture and concentrate dark matter, heating up in ways we could detect. The search has turned into a kind of cosmic triangulation, with each failure not as a setback but as a step forward. Every experiment that doesn't find dark matter tells us where not to look, refining the search like a sculptor chiseling away marble to reveal the shape beneath. We may not know what dark matter is yet, but we're learning what it isn't, and that's progress. The universe's greatest architect is still hiding, but the hunt is far from over. If anything, the stakes are higher than ever, because solving this mystery wouldn't just fill a gap in our textbooks, it would rewrite them. What if dark matter isn't the answer at all? A small but passionate group of scientists argues we've been chasing a phantom, that the real solution lies not in invisible particles, but in rewriting the laws of gravity themselves. This bold idea, known as modified Newtonian dynamics or MUND, suggests that gravity doesn't weaken as quickly over vast distances as Newton or Einstein predicted. Instead, it lingers just enough to explain why stars on the edges of galaxies orbit faster than expected. No dark matter required. Picture a car speeding around a curve. Newton says it should fly off unless held by an unseen force, but MUND claims the road itself bends differently at high speeds, keeping the car on track naturally. The appeal of MUND lies in its simplicity. Why invent an entirely new form of matter when tweaking existing equations might do the trick? Proponents point to stunning successes, like accurately predicting the rotation of hundreds of galaxies using MUND-adjusted math, a feat dark matter models often struggle with unless finely tuned. There's an elegance to this approach, a reluctance to populate the cosmos with invisible entities when the answer might be hiding in plain sight, encoded in the laws we thought we knew. But elegance isn't always enough. The Bullet Cluster, a cosmic collision where dark matter and visible gas were wrenched apart, delivers a brutal blow to MUND. Here, gravity's pull clearly comes from regions where no visible matter exists, precisely what dark matter predicts. MUND struggles to explain this without adding hidden mass back into the mix, blurring its initial promise. Similarly, the cosmic web, the vast, filamentary structure of the universe, aligns perfectly with dark matter simulations, but leaves MUND scrambling to catch up. Yet the debate is far from settled. Some researchers are refining MUND into even more sophisticated theories, like tensor vector scalar gravity, which introduces subtle new forces to account for these gaps. Others explore hybrid models where dark matter and tweaked gravity coexist, a cosmic compromise. What's fascinating isn't just the science, it's the philosophy. This rivalry embodies science at its best, a clash of worldviews where every observation is a battleground, and even Einstein's legacy isn't sacred. At its heart, this isn't just about equations or galactic rotations. It's about how we confront the unknown. Do we fill the gaps with new entities, or do we question the framework itself? Both paths have led to revolutions before. Neptune was discovered because Newton's gravity predicted an unseen planet tugging on Uranus. Mercury's wobble, though, couldn't be explained by hidden mass. It demanded Einstein's radical rethinking of gravity. History whispers that sometimes the answer isn't in the shadows, but in the light we've been misreading all along. For now, the scales tip toward dark matter, but the door is open. Every unexplained anomaly, like galaxies mysteriously devoid of dark matter or odd gravitational lenses, fuels the fire. The truth, as always, will lie in the data. And until then, this debate reminds us that science progresses not by consensus, but by the relentless questioning of even our most cherished assumptions. After all, the universe owes us no favors. It hides its secrets well, whether in the darkness between stars or the fine print of the laws we thought we'd mastered. The Bullet Cluster isn't just a pair of colliding galaxies, it's a cosmic crime scene. and the evidence left behind is undeniable. Picture two massive galaxy clusters, each containing hundreds of galaxies, barreling into one another at millions of miles per hour. When they collided, the ordinary matter, the hot gas that makes up most of their visible mass, slammed together like two clouds of smoke, heating up and glowing brightly in X-rays. But something else happened, something far more revealing. The dark matter within these clusters didn't slow down or collide. It kept right on moving, passing through the chaos as if it weren't even there. This left a stunning separation, the visible gas trapped in the center like debris after a car crash, while the dark matter, detected only by its gravitational lensing effect, continued on its path, hovering on either side of the collision. That separation is the smoking gun. If dark matter behaved like normal matter, it would have pooled with the gas. Instead, it proved itself to be truly ghostly, interacting only through gravity, untouched by the forces that govern everything else we can see. What makes the bullet cluster so compelling isn't just the observation itself, but what it means for our understanding of the universe. This wasn't a theoretical prediction or a computer simulation. It was real, observable proof that dark matter exists as a distinct, invisible entity. When astronomers mapped the lensing patterns around the cluster, they found peaks of gravitational distortion precisely where no visible matter existed, a fingerprint left behind by the unseen. Critics of dark matter, including proponents of modified gravity theories, have struggled to explain this observation. Mund, for instance, would predict that gravity's pull should align with the visible gas, not separate from it. Yet the bullet cluster shows us unequivocally that gravity's source isn't where the light is, it's where the darkness lingers. But the story doesn't end there. The bullet cluster also reveals something profound about dark matter's nature. The fact that it didn't collide or slow down tells us its particles, whatever they are, must be extraordinarily aloof. Unlike protons or electrons, which constantly bump into one another, dark matter particles seem to ignore everything except gravity. This collisionless behavior explains why dark matter forms vast, diffuse halos around galaxies rather than clumping into stars or planets. It's a cosmic loner, drifting through the universe without leaving a trace except for the immense gravitational wake it leaves behind. The implications ripple far beyond this single collision. If dark matter can pass through itself and normal matter without slowing, then it must be incredibly abundant to have the gravitational muscle we observe. That fits perfectly with what we see in simulations of the early universe, where dark matter's gravity laid the scaffolding for galaxies to form. It also suggests that dark matter isn't just a passive bystander, it's an active architect shaping the cosmos in ways we're only beginning to decode. Yet for all we've learned, the bullet cluster raises as many questions as it answers. Why does dark matter interact so weakly with everything else? What kind of particle could possibly be so indifferent to the forces that bind our visible world? And if it's truly everywhere, why does it refuse to reveal itself outside of gravity's shadow? This cosmic collision is more than just evidence, it's a challenge. A challenge to our theories, our experiments, and our imagination. Because if something as fundamental as dark matter can hide in plain sight, what else might the universe be keeping from us? The bullet cluster is a reminder that nature's greatest mysteries aren't always hidden in the distant past or the farthest reaches of space. Sometimes they're written in the aftermath of a cosmic wreck, waiting for us to piece together the clues. Zoom out far enough, and the universe reveals its true structure not as a scattering of isolated galaxies, but as an intricate network of light and shadow, a cosmic spiderweb stretching across billions of light years. This is the large-scale structure of the universe, and its threads aren't made of silk but of dark matter. Simulations like the Millennium Run show us how it works. start with a universe filled with dark matter's faint gravitational ripples left over from the Big Bang, then let physics run its course. Over billions of simulated years, those ripples grow into vast filaments, intersecting at dense nodes where galaxy clusters glow like cities at night. The voids between them, not empty but eerily still, dark matter's gravitational valleys where matter never pooled. What's astonishing is how perfectly these simulations match reality. When astronomers map the positions of millions of galaxies, they find them precisely where the models predict, strung along dark matter's invisible highways. The Sloan Digital Sky Survey, for instance, revealed a cosmic web so vast it takes up a quarter of the visible sky, with galaxies clustering into walls and filaments that mirror the simulations down to the smallest details. It's as if we've uncovered the universe's hidden skeleton, a scaffolding built by dark matter's gravity over 13 billion years. But how does something invisible create something so tangible? Think of dark matter as the universe's first artist. In the early cosmos, ordinary matter was too hot and energetic to clump together, but dark matter, unaffected by heat or light, could quietly gather under its own gravity. Wherever dark matter formed a slight overdensity, it pulled in more dark matter, then gas, then eventually the seeds of galaxies. Over time, these patches grew into filaments, their gravitational pull channeling galaxies into sprawling networks. The cosmic web isn't just a structure, it's a record of dark matter's patient work, a fossil of gravity's slow dance. The scale of this web is almost impossible to grasp. Filaments can stretch for hundreds of millions of light years, weaving through the cosmos like threads in a tapestry. At their intersections, galaxy clusters swarm with thousands of members, each one held in place by dark matter's grip. Meanwhile, the voids between filaments are staggeringly empty, some so devoid of matter that if you stood in one, the night sky would be nearly black, with only the faintest glow of distant galaxies to remind you the universe exists at all. Yet even in these voids, dark matter leaves its mark. Recent studies suggest they're not completely empty, but contain faint, diffuse galaxies, one so dim they've evaded detection until now. These ghost galaxies might be the universe's failed experiments, places where dark matter's pull wasn't quite strong enough to spark robust star formation. They're the shadows of the cosmic web, reminders that dark matter's influence is everywhere, even where almost nothing else is. This grand structure isn't static. The cosmic web is still evolving, with dark matter filaments funneling galaxies toward clusters in a slow-motion river of stars. In billions of years, our own Milky Way will be drawn into the Virgo cluster, merging with others in a celestial metropolis. Dark matter's web isn't just shaping the universe, it's writing its future, and as we map more of its threads, we're not just charting the cosmos, we're reading the story of how everything, including us, came to be. Galaxies spin like cosmic carousels, but their motion holds a secret that upended our understanding of the universe. In the 1970s, astronomer Vera Rubin pointed her telescope at the Andromeda Galaxy, expecting to see a predictable pattern, stars near the center whirling quickly, like skaters pulling into a tight spin, while those farther out slowed down, just as planets orbit more lazily the farther they are from the sun. But the data told a different story. Stars at the galaxy's edge raced just as fast as those near the core, as if some invisible hand were gripping them, preventing them from flying off into the void. This wasn't just a quirk of Andromeda. Every spiral galaxy Rubin studied revealed the same defiance of gravity's rules, a cosmic rebellion that couldn't be explained by the glow of stars or the haze of interstellar gas alone. The implications were staggering. According to Newton's laws, the speed of orbiting stars should drop off with distance. a principle Kepler had nailed down centuries earlier when describing planetary motion. If galaxies held only the mass we could see, their outer stars would be moving so slowly they'd drift away, like marbles escaping a child's spinning plate. Yet there they were, clinging to their breakneck orbits, held fast by something unseen. Rubin's calculations revealed the truth. Galaxies must contain at least 6 times more mass than their visible light betrayed, an invisible halo of matter whose gravity extended far beyond the luminous edges of the galactic disk. This missing mass wasn't just a small oversight, it was the dominant ingredient in the cosmic recipe. Picture a snow globe where the glitter represents stars and gas swirling in water. Now imagine the water itself is replaced with an invisible, syrup-thick fluid, its weight dictating the glitter's motion. That's dark matter's role in galaxies, unseen, omnipresent, and utterly essential. Without it, galaxies would unravel, their stars scattering like sparks from a pinwheel. Rubin's discovery didn't just hint at dark matter, it handed us a map of its distribution. Those flat rotation curves, where orbital speeds stay constant regardless of distance, revealed something extraordinary. Dark matter isn't concentrated in the galaxy's core like stars are. Instead, it forms an enormous diffuse sphere, a halo that engulfs the entire visible galaxy, thinning out gradually over vast distances. This explained why stars on the outskirts felt such a strong pull. They were swimming in an ocean of invisible mass, one that dwarfed the galaxy's shining core. But here's the twist: dark matter halos aren't just passive containers. They actively shape galaxies from birth. Computer simulations show that without these halos, gas clouds in the early universe would never have collapsed into the dense knots needed to ignite stars. Dark matter's gravity provided the scaffolding, the cosmic framework upon which ordinary matter could gather and glow. Even today, the halos act like gravitational anchors, stabilizing galaxies against the turbulence of cosmic collisions and the relentless tides of neighboring clusters. The mystery deepens when we consider outliers, galaxies like NGC 1052, where stars orbit so slowly they seem to defy dark matter's grip, or others where rotation curves spike unexpectedly. These anomalies aren't contradictions, they're clues. Some galaxies might have lost their dark matter in violent encounters, like trees stripped of leaves in a storm. Others could be shrouded in warm, dark matter, particles moving fast enough to smooth out halos into gentler gradients. Each exception forces us to refine the rules, to ask whether dark matter is even more complex than we imagined. What's remarkable is how a simple observation, the way stars move, unlocked one of cosmology's greatest puzzles. Rubin's work didn't just prove the existence of dark matter, it showed us where to look for its fingerprints, from the whirl of distant galaxies to the grand architecture of the cosmic web. Those rotation curves are more than data points. They're the silent testimony of an invisible universe, whispering its secrets to anyone patient enough to listen. And the conversation is far from over. With every new galaxy mapped, every curve measured, we're deciphering the hidden language of gravity, one orbit at a time. To understand dark matter's role in the early universe, we have to rewind to its oldest surviving snapshot, the cosmic microwave background, or CMB. This faint glow, lingering from just 380,000 years after the Big Bang, is more than a relic. It's a detailed blueprint of the infant cosmos. When scientists map the CMB's minute temperature variations, fluctuations as subtle as 1 part in 100,000, they're seeing the seeds of all cosmic structure. And those seeds were planted by dark matter. Imagine the early universe as a pot of simmering water, with bubbles of slightly denser matter rising and falling. Ordinary matter, protons, electrons, and light was trapped in a chaotic dance, constantly buffeted by radiation pressure. But dark matter, unaffected by light's push, could quietly pool under its own gravity, creating gravitational wells where ordinary matter would eventually settle. The CMB captures this moment, its patterns revealing where dark matter had already begun stitching the fabric of the cosmos. Without these invisible scaffolds, galaxies wouldn't have formed for billions of years, if at all. The universe would be a featureless void, its matter too scattered to ignite stars. The precision of these measurements is staggering. ESA's Planck satellite mapped the CMB with such sensitivity that it detected dark matter's gravitational imprint in the way these temperature fluctuations are spaced, like finding the shadow of a hidden hand in the brushstrokes of a painting. The data shows dark matter wasn't just present, it was dominant, outweighing ordinary matter 5-1 even in those first moments. Its gravity dictated how matter clumped, setting the stage for everything that followed. What's even more remarkable is how these ancient fluctuations align with the universe we see today. The denser patches in the CMB match the locations of modern galaxy superclusters, as if the cosmos followed a script written in its infancy. Simulations that start with the CMB's initial conditions adding dark matter's gravitational pull accurately predict the sprawling cosmic web we observe, complete with its filaments and voids. It's a continuity spanning billions of years, a thread connecting the universe's birth to its present structure. Yet the CMB also holds puzzles. Some fluctuations are fainter or more pronounced than theories predict, hinting that dark matter's behavior might be more complex than we've assumed. Could it interact with itself in ways we haven't accounted for? Or might there be multiple types of dark matter, each leaving a different mark on the early universe? These aren't just academic questions, they're keys to understanding why the cosmos evolved the way it did, and what its ultimate fate might be. The CMB reminds us that dark matter isn't a latecomer to the cosmic story. It was there from the beginning, shaping the universe before the first stars flickered to life. Its fingerprints are everywhere in the afterglow of creation, in the spin of galaxies, in the vast web connecting all things. And as we keep studying that ancient light, we're not just looking back in time. We're deciphering the instructions that built reality itself, deep underground where the Earth itself acts as a shield against cosmic interference. Scientists have built the quietest rooms in history, not to escape noise, but to listen for the faintest whisper of the universe's most elusive substance. These aren't ordinary labs, they're ultra-sensitive traps designed to catch dark matter in the act. Picture a vat of liquid xenon, so pure it's practically flawless, chilled to temperatures colder than deep space. Surrounding it are layers of shielding water, lead, even copper mined from ancient shipwrecks to avoid modern radioactivity. The goal, to create an environment so still, so silent, that if a single dark matter particle grazes an atomic nucleus, the detector will notice. The principle is simple, but the execution is a masterpiece of engineering. When a dark matter particle, hypothetically a WIMP, or weakly interacting massive particle collides with a xenon or argon nucleus, it should produce a tiny flash of light and a ripple of electric charge. These signals are unimaginably faint, equivalent to detecting a single raindrop hitting a lake during a hurricane. That's why these experiments are buried beneath miles of rock, where the Earth's crust filters out cosmic rays and other false alarms. Places like Italy's Gran Sasso Laboratory, South Dakota's Sanford Underground Research Facility, or China's Jinping Underground Laboratory aren't just locations, they're fortresses against interference, built to hear the universe's quietest notes. Yet after decades of searching, the detectors remain stubbornly silent, but silence isn't failure. Every null result narrows the possibilities, like a detective crossing suspects off a list. Experiments like LUX Zeppelin, Xenon 1T, and Panda X have ruled out entire classes of potential dark matter particles, pushing theorists to refine their models. It's a process of elimination on a cosmic scale, where each experiment sets stricter limits, cornering dark matter into an ever-shrinking box of plausible properties. The stakes couldn't be higher. A definitive detection wouldn't just solve a mystery, it would open a door to an entirely new branch of physics. Imagine confirming that dark matter is a WIMP, a particle born in the early universe's fury, now drifting through your hand as you watch this video. Or discovering it's something stranger, like an action, a particle so lightweight it behaves more like a wave than a solid speck. Each possibility rewrites our understanding of reality, revealing that the universe is far richer, far weirder than we ever dreamed. But what if dark matter isn't just hiding? What if it's fundamentally invisible to our current tools? Some theories suggest dark matter might interact with ordinary matter through forces we haven't discovered yet, making it undetectable by conventional means. Others propose it's fuzzy, spread out like a quantum fog rather than discrete particles. These ideas aren't science fiction. They're driving the next generation of experiments, from detectors tuned to lower energies to networks of atomic clocks that might feel dark matter's passage through subtle changes in time itself. This isn't just a technical challenge, it's a philosophical one. How do you search for something when you don't know what it looks like, how it behaves, or even if it wants to be found? The answer lies in perseverance and creativity. Every detector upgrade, every new material, every tweak to the shielding is a step closer to the unknown. And when, not if the first clear signal appears, it won't just be a discovery. It'll be a revolution, proving that the universe's greatest architect is finally ready to reveal itself. If we can't catch dark matter directly, maybe we can catch its fingerprints, the aftermath of its unseen collisions. Across the cosmos, when dark matter particles crash into one another, theorists predict they might annihilate in a burst of energy, releasing gamma rays, neutrinos, or even antimatter as their final calling card. It's like tracking a criminal by following the trail of spent shell casings rather than the suspect themselves. This is the essence of indirect detection, searching not for dark matter, but for the echoes of its existence. At the heart of this hunt is NAS, a Fermi gamma-ray space telescope, silently orbiting Earth with its instruments trained on the sky's most promising targets. One such hotspot, the center of our Milky Way, where dark matter is thought to pile up in staggering densities, drawn in by the supermassive black hole's immense gravity. If dark matter annihilates anywhere, it should be here, a cauldron of invisible particles colliding and transforming into gamma rays. Fermi has indeed spotted an excess of gamma rays emanating from the galactic center, a tantalizing hint that could be dark matter's signature. Yet the puzzle isn't so simple. The same region crackles with pulsars, supernova remnants, and other astrophysical phenomena that also produce gamma rays. Teasing apart dark matter's potential signal from this cosmic cacophony is like trying to hear a single violin in a symphony orchestra. Meanwhile, beneath the Antarctic ice, another experiment takes a different approach. The Ice Cube Neutrino Observatory isn't looking for gamma rays, it's searching for neutrinos, nearly massless particles that streak through the universe unimpeded. If dark matter decays or annihilates in distant galaxies, the resulting neutrinos could travel billions of light years before plunging through the Earth and lighting up Ice Cube's sensors. In 2013, the observatory detected high-energy neutrinos with no obvious source, sparking speculation that dark matter might be the culprit. But like Fermi's gamma rays, the evidence remains circumstantial, a maybe rather than a eureka. Then there's the Alpha Magnetic Spectrometer, mounted on the International Space Station, which hunts for antimatter particles like positrons in cosmic rays. Some models suggest dark matter annihilations could produce a surge of these particles, and intriguingly, AMS has found more positrons than expected at certain energies. Yet again, alternative explanations like pulsars cloud the picture. The challenge isn't just finding anomalies, it's proving they couldn't come from anything else. What makes indirect detection so compelling is its creativity. When one door slams shut, science finds a window. If dark matter refuses to show itself directly, we'll study the ripples it leaves in cosmic ponds, the shadows it casts on gamma-ray maps, the whispers it sends via neutrinos. Every unexplained signal, every anomalous excess, is a piece of the puzzle even if we don't yet know how they fit together. And while none of these hints have solidified into proof, they've painted a portrait of possibility, narrowing the search to the most promising corners of theory and observation. The beauty of this approach lies in its sheer scope. Unlike underground labs confined to a few tons of detector material, indirect searches harness the entire universe as their testing ground. From the depths of space to the ice of Antarctica, from the orbit of the ISS to the hearts of galaxies, the hunt for dark matter's echoes turns the cosmos itself into a laboratory. And somewhere in the data, amid the gamma rays, neutrinos, and antimatter, the truth may be hiding, waiting for the right combination of patience, ingenuity, and luck to reveal itself. Black holes and dark matter, two of the universe's greatest enigmas, might be hiding a secret connection. Imagine the dawn of time, when the cosmos was a seething cauldron of energy. In that chaos, some scientists believe tiny black holes could have formed, not from collapsing stars but from the sheer density of the infant universe itself. These primordial black holes, some no larger than an atom but as massive as a mountain, might still lurk in the darkness today, invisible yet everywhere. If they exist in staggering numbers, they could be the elusive dark matter we've been chasing all along. It's a radical idea that the missing mass of the universe isn't a particle at all, but a sea of ancient black holes woven into the fabric of space since the beginning. But how would we even know? Gravitational waves might hold the answer. When black holes collide, they send ripples through spacetime, ripples we can now detect with observatories like LIGO and Virgo. If primordial black holes are out there, their mergers could produce a unique fingerprint in the gravitational wave background, a faint hum of collisions happening all around us. Some researchers are scouring the data for signs of unusually light black holes, ones that don't fit the typical stellar mass or supermassive categories. Others are looking for telltale microlensing events, brief flashes of light when a hidden black hole passes in front of a star, warping its glow like a cosmic magnifying glass. Yet not all black holes are primordial, and even ordinary ones might interact with dark matter in extraordinary ways. Picture a supermassive black hole at the center of a galaxy, its gravity so intense that it pulls in dark matter like a whirlpool. Over time, dark matter could accumulate around it, forming a dense, invisible halo. This isn't just theoretical. Some models suggest these halos could grow so massive they alter the black hole's behavior, subtly changing how it spins or how it merges with others. The Event Horizon Telescope, famous for capturing the first image of a black hole's shadow, might one day detect these dark matter halos indirectly through their gravitational influence on the surrounding light. The most tantalizing clues come from the edges of our understanding. Take the mysterious, too big to fail problem. Some galaxies seem to have fewer satellite galaxies than dark matter simulations predict. But if dark matter is tied to black holes, their gravitational kicks could have scattered these satellites, leaving behind a cosmic breadcrumb trail. Or consider Hawking radiation, the faint glow predicted to leak from black holes as they evaporate. If dark matter is made of black holes, their collective evaporation might leave an imprint on the cosmic microwave background, a whisper from the universe's first moments. This intersection of black holes and dark matter isn't just about solving two puzzles at once, it's about rewriting the rules. If primordial black holes are dark matter, it challenges our ideas about particle physics, forcing us to rethink what the universe is made of. If dark matter halos surround black holes, it could explain why some galaxies evolved differently than expected. And if neither idea pans out, the search itself pushes our technology and theories to new heights, proving that even the universe's best-kept secrets can't hide forever. Every observation, every gravitational wave, every flicker of light at the edge of a black hole is a potential clue, waiting to reveal whether these cosmic giants are the architects of the darkness or something even stranger. The hunt for dark matter is entering its most thrilling chapter yet, as a new generation of tools prepares to pry open the universe's best-kept secret. Leading the charge is the Vera Rubin Observatory, perched high in Chile's Atacama Desert. When its massive mirror, the width of a tennis court, scans the sky, it won't just capture images, it will create a time lapse of the cosmos, tracking billions of galaxies over a decade. Each snapshot will reveal how dark matter's gravity tugs at starlight, warping galaxy shapes in ways too subtle for the human eye, but unmistakable to Rubin's precision instruments. This isn't just mapping, it's forensic reconstruction, piecing together the architecture of the invisible universe at a scale never before attempted. Meanwhile, floating 1,000,000 miles from Earth, the Euclid Space Telescope is taking a different approach. Instead of watching galaxies move, Euclid studies their distortions, a phenomenon called cosmic shear. Imagine pressing your finger against a stretched rubber sheet. The way it warps reveals the pressure you apply. Dark matter does the same to spacetime, bending the light from distant galaxies into delicate arcs. Euclid's wide-field camera captures these distortions across a third of the sky, compiling a 3D dark matter map so detailed it could pinpoint hidden filaments thinner than a single pixel in previous surveys. Together, Rubin and Euclid form a tag team of cosmic cartography, one tracking motion, the other mapping deformation. Their combined data painting the most complete picture yet of dark matter's distribution. But telescopes alone won't crack this case. Beneath the Swiss-French border, the upgraded Large Hadron Collider is preparing to smash protons with unprecedented energy, probing for dark matter particles that might flicker into existence during collisions. Unlike earlier runs, these experiments will hunt not just for WIMP but for a zoo of theoretical particles actions, sterile neutrinos, even hypothetical dark photons that might mediate dark matter's interactions. It's a brute force strategy. If dark matter is hiding in the subatomic shadows, the LHC's collisions might shake it loose. Back underground, next-generation detectors are pushing sensitivity to near impossible limits. The LUX Zeppelin experiment's liquid xenon chamber now watches for dark matter with a vigilance akin to sensing a single grain of sand dropped into an Olympic swimming pool. Darwin, a proposed successor, aims to be 100 times more sensitive, its chamber so pure it could detect a dark matter particle passing through once a century. These aren't just incremental upgrades, they're quantum leaps, each one narrowing the hiding places where dark matter could linger, the stakes nothing less than rewriting physics. If dark matter is a particle, its discovery would unveil a whole new sector of nature, potentially explaining why the universe has mass at all. If it's primordial black holes, we'll need to rethink cosmic evolution. And if it's something beyond our current theories that could upend relativity, quantum mechanics, or both, the next decade promises answers but also deeper questions. Because in this grand cosmic detective story, Every clue leads not just to dark matter's identity, but to a fuller understanding of reality itself. The silent architects may have stayed hidden for 13 billion years, but their walls are beginning to tremble. Dark matter has long been the stuff of legends, not just in scientific journals, but in the stories we tell ourselves about the cosmos. From the glowing veins of fictional, dark drives in sci-fi epics to the ominous energy waves threatening planets in blockbuster films, pop culture loves to dress up this mystery in flashy, dramatic costumes. Take Marvel's Doctor Strange, where dark matter becomes a weapon capable of unraveling dimensions, or the eerie void in video games like Destiny, where it's a malevolent force lurking beyond human comprehension. These portrayals are thrilling, but they're also telling because they reveal something deeper about us. When writers and artists reach for metaphors to describe the unknown, they keep grabbing for dark matter, as if it's the ultimate symbol of the universe's hidden power. But here's the twist: reality is stranger than fiction. Dark matter isn't a glowing energy source or a universe-ending threat. It's something far more subtle, far more pervasive. While Hollywood imagines it as a tool or a terror, scientists see it as the silent scaffolding holding galaxies together, the unseen hand guiding the cosmos. The gap between these two versions, the dramatic and the factual, is where curiosity thrives. Think of it like this: if pop culture is a fireworks display, science is the slow, patient unraveling of why the sky is dark between the sparks. Both are beautiful, but only one reveals the true nature of the universe. This dance between imagination and discovery isn't just entertaining, it's educational. When a teenager watches a spaceship fueled by dark matter in a movie, it might spark a question: wait, is that real? That moment of curiosity is a gateway. Suddenly, the real science, the painstaking work of physicists studying gravitational lensing or building underground detectors, becomes a little more relatable. It's no accident that some of today's leading astrophysicists trace their passion back to a sci-fi book or a late-night rerun of Star Trek. Fiction doesn't just entertain, it plants seeds. Yet there's a responsibility in this storytelling. When dark matter is reduced to a magical MacGuffin, it risks obscuring the real wonder that our universe is built on mysteries we're still learning to name. The truth doesn't need embellishment. The fact that we're made of atoms, yet surrounded by something 6 times more abundant that we can't see, touch, or explain, that's already the plot of the greatest story ever told. The real drama isn't in fictionalized doom scenarios. It's in the quiet persistence of scientists staring at data, knowing the answer is hiding just beyond the light. Perhaps that's the most inspiring lesson of all. Dark matter in pop culture reflects our hunger for adventure, but the real quest, the one happening in labs and observatories, is about humility. It's about admitting we don't have all the answers and that the universe owes us none. Every glowing sci-fi nebula, every ominous dark energy weapon is a reminder that the unknown isn't something to fear or fictionalize, it's an invitation. And somewhere, right now, a kid watching a superhero movie is about to discover that the real universe is even cooler than the stories. They might just be the one to finally tell us what's hiding in the dark. Every great scientific quest carries a question: at what cost? The search for dark matter is no exception. With billions of dollars funneled into underground detectors, space telescopes, and particle colliders, some wonder if this pursuit is a luxury we can't afford, especially when Earth's own problems demand urgent attention. But science rarely fits neatly into spreadsheets. The same curiosity that drives us to decode dark matter has historically unlocked unforeseen revolutions. Consider how quantum mechanics, once an esoteric theory about atomic behavior, birthed the transistors powering every smartphone, or how Einstein's equations, scribbled in solitude, later enabled GPS satellites to guide billions. Dark matter research isn't just about mapping the invisible, it's about planting seeds for technologies we can't yet imagine. Yet the stakes go beyond practical applications. Understanding dark matter reshapes our cosmic self-awareness. For centuries, humanity saw itself as the center of creation, surrounded by a static, knowable universe. Today, we grapple with the humbling truth that we're made of mere crumbs, the 5% of matter that isn't dark. Unraveling this mystery isn't vanity, it's a fundamental redefinition of our place in existence. When Galileo pointed his telescope at Jupiter's moons, he didn't just discover celestial bodies, he dismantled an entire worldview. Dark matter promises a similarly seismic shift, revealing whether we're floating on a raft of visible matter in an ocean of something stranger. But here's the ethical tightrope. This knowledge shouldn't belong to a privileged few. The instruments probing dark matter, from Chile's mountaintop observatories to CERN's sprawling colliders, are funded by public money across nations. Their discoveries must remain a global commons, not a corporate patent or military secret. History warns us what happens when science becomes siloed. The atomic bomb's creation, though rooted in pure physics, altered geopolitics forever. Dark matter's potential applications, while speculative, could be equally transformative, perhaps revealing new energy sources or propulsion methods. Ensuring equitable access isn't just idealism, it's a safeguard against inequality masquerading as progress. Collaboration is already lighting the way. Projects like the Rubin Observatory share data openly, while the Square Kilometre Array radio telescope pools resources from 16 countries. These efforts prove that humanity's biggest questions can unite rather than divide us. Yet challenges remain. When a breakthrough comes, will it deepen existing divides or foster shared purpose? The answer depends on choices we make today: funding structures, data policies, and a commitment that the cosmos belongs to everyone. At its core, the ethical imperative isn't just about finding dark matter. It's about who we become in the process. Do we channel our collective resources into a quest that elevates human understanding, or retreat into short-term pragmatism? The universe doesn't owe us answers, but it does offer this choice to reach beyond what's visible together. What if dark matter isn't just hidden? What if it's from somewhere else entirely? Picture our universe as a sheet of paper floating in a vast, multidimensional space. Now imagine other sheets, parallel universes hovering just out of reach, each with its own laws of physics, its own stars, its own life. In this mind-bending scenario, dark matter could be the ink bleeding through from another page, a subtle trace of worlds beyond our own. This isn't science fiction. It's a serious theory called the brain-world model, where our reality is a three-dimensional brain drifting in a higher dimensional bulk. And dark matter, it might be the gravitational echo of a neighboring universe, leaking into ours like light under a doorway. The math behind this idea is as elegant as it is strange. In some versions of string theory, particles in other brains could exert gravity on ours without any other interaction, making them invisible yet influential, exactly how dark matter behaves. It's like feeling the breeze from a window you can't see, knowing something must be there even if it's beyond your perception. These theories don't just explain dark matter's ghostly nature, they redefine it. Instead of a missing particle, dark matter becomes a cosmic neighbor, its presence a clue to realities we've yet to imagine. Critics argue this is speculation run wild, and they're not wrong. Without direct evidence, multiverse theories remain in the realm of beautiful possibilities. But consider this: if dark matter truly is a visitor from another dimension, its distribution might carry hints of its origin. Some researchers suggest looking for unusual patterns in dark matter's cosmic web filaments that seem to align in ways our physics can't explain, or voids that defy gravitational logic. Others propose that colliding brains could leave scars in the cosmic microwave background, faint imprints of a multiversal handshake. The boldest experiments aim to test these ideas right here on Earth. Particle accelerators like the Large Hadron Collider might, by sheer energy, create microscopic black holes, brief portals to extra dimensions. While none have appeared yet, their discovery would shake the foundations of physics, proving there's more to space than length, width, and height. Meanwhile, gravitational wave observatories listen for ripples that don't match known astrophysical events, whispers of brain collisions or higher dimensional vibrations. Even if the multiverse connection remains unproven, the pursuit changes how we see dark matter. No longer just a puzzle to solve, it becomes a lens, a way to question whether our universe is alone, whether gravity is the only force bridging realities, whether the cosmos is vaster than we dared to dream. The irony is delicious. The very substance that makes up most of our universe might not belong here at all. And if that's true, then dark matter isn't just shaping galaxies. It's pointing the way to frontiers we're only beginning to glimpse. There's something profoundly unsettling and exhilarating about the idea that most of the universe is invisible to us. Dark matter doesn't just defy detection, it challenges the very foundations of how we understand reality. For centuries, science operated on a simple principle. If something exists, we should be able to observe it, measure it, test it. But dark matter laughs in the face of that assumption. It's like trying to study a ghost by the way it moves the curtains. We see the effects, but the thing itself remains stubbornly out of view. This isn't just a technical hurdle, it's a philosophical earthquake. How much of reality exists beyond the limits of our perception? And if we can't see it, touch it, or interact with it, how can we ever truly know it's there? History offers a humbling parallel. 2 centuries ago, atoms were just as elusive as dark matter is today. Scientists like John Dalton proposed their existence to explain chemical reactions, even though no one could see them. Critics dismissed atoms as mathematical conveniences, placeholders for gaps in knowledge. It wasn't until Einstein's paper on Brownian motion in 1905 that atoms moved from theory to fact, their reality inferred by the jittering of pollen grains in water. Dark matter is following a similar path. We don't have direct proof yet, but the cosmic evidence, from galaxy rotations to gravitational lensing, paints a picture so compelling that doubting it would require rewriting the laws of physics. The lesson here is patience. Reality often reveals itself in layers, and the deepest truths are rarely the most obvious. This quest forces us to confront the limits of human intuition. Our brains evolved to navigate a world of medium-sized objects moving at medium speeds, not the bizarre realms of quantum uncertainty or invisible cosmic scaffolds. Dark matter doesn't just resist observation, it resists imagination. Try picturing something that doesn't absorb, reflect, or emit light, that passes through solid matter like wind through a screen door, yet whose gravity sculpts galaxies. It's like describing silence by the shape of the space between musical notes. And yet, here we are, building detectors the size of buildings, launching telescopes into orbit, all to chase shadows. There's a kind of poetry in that a species of apes who climbed down from trees now wrestling with the architecture of existence itself. The philosophical implications run deep. If dark matter is confirmed, it will mean that the universe is fundamentally different from how it appears, that what we see is just the froth on an ocean of unseen forces. This isn't just about adding a new particle to the textbooks, it's about recalibrating our place in the cosmos. We're not the center of the universe, nor are we even made of its primary substance. We're the exception, not the rule. That realization carries a quiet awe, a reminder that science isn't just about answering questions, but about learning which questions to ask. Perhaps the most radical idea of all is that dark matter might not be the only invisible player. Could there be other hidden layers of reality, equally influential but even more elusive? The search for dark matter has already birthed new branches of physics, from supersymmetry to extra dimensions. Each dead end, each unexpected result isn't a failure. It's a signpost pointing toward stranger possibilities. The universe, it seems, is far richer than our senses can grasp, and that's the real gift of this mystery. Not just the answers we might find, but the humility to accept how much we have yet to discover. After all, the greatest scientific revolutions often begin with the simple admission that we've been missing something right in front of us, or in this case, all around us, the whole time. The Standard Model of particle physics is one of humanity's greatest intellectual triumphs, a meticulous blueprint that explains everything from the glow of a light bulb to the nuclear fusion powering the sun. It catalogs all known particles, from the humble electron to the elusive neutrino, and the forces that govern their interactions with breathtaking precision. Yet for all its brilliance, the Standard Model has a glaring blind spot. It leaves no room for dark matter. Not a single particle in its carefully constructed framework matches the properties of this cosmic enigma. That absence isn't just a minor oversight. It's a flashing neon sign pointing to undiscovered physics, a realm beyond the equations we've relied on for decades. This gap isn't just puzzling, it's exhilarating. The Standard Model's inability to explain dark matter suggests we're standing at the edge of a much larger theoretical landscape, one where entirely new particles or even undiscovered dimensions might exist. Take supersymmetry, for instance, a leading candidate for extending the Standard Model. It proposes that every known particle has a heavier, invisible superpartner. Some of these shadowy twins could be stable enough to persist from the Big Bang to today, drifting through the cosmos as dark matter. If proven, supersymmetry wouldn't just solve the dark matter riddle, it would unify the fundamental forces in a way Einstein dreamed of, bridging quantum mechanics and gravity under a single elegant framework. Then there's the possibility of extra dimensions, hidden realms curled up so tightly we can't perceive them, yet whose gravitational influence might leak into our universe as dark matter. Imagine ants crawling on a sheet of paper, oblivious to the third dimension above them. If gravity were sensitive to higher dimensions, its apparent weakness compared to other forces could be explained by its dilution across these unseen layers. Dark matter might be the gravitational echo of particles moving through these hidden spaces, tugging on our reality from beyond the veil. The stakes couldn't be higher. Discovering dark matter's identity wouldn't just fill a gap in a textbook, it could crack open the door to a grand unified theory, a theory of everything that reconciles the quantum realm with cosmic-scale gravity. Picture the fragments of a shattered vase. The Standard Model explains some pieces, general relativity others, but dark matter might be the glue that fits them together. Its particle, whether a WIMP, an action, or something stranger, could reveal connections between forces we've long thought were separate, rewriting our understanding of reality's deepest rules. But here's the catch. Every time physicists stretch the Standard Model to accommodate dark matter, the universe throws back a challenge. The Large Hadron Collider's failure to find supersymmetric particles has left theorists scrambling. Actions, though promising, remain frustratingly elusive. Some researchers are now exploring even wilder ideas, like dark sectors, entire families of particles interacting only weakly with ours, forming a parallel universe of invisible matter right under our noses. Others suggest dark matter might not be a particle at all, but a macroscopic object, primordial black holes, or even exotic, planet-sized lumps of dense matter left over from the Big Bang. This isn't just academic noodling. Each hypothesis carries profound implications. If dark matter is a WIMP, it implies a cosmic symmetry tying all forces together. If it's an action, it could solve two mysteries at once: dark matter and why the strong nuclear force behaves so curiously, and if it's something outside all current frameworks. That would be the most thrilling outcome of all, a signal that the universe is far stranger than our boldest theories dared to suggest. The Standard Model's silence on dark matter isn't a failure, it's an invitation. Just as Newtonian physics gave way to relativity and classical mechanics to quantum theory, we may be on the verge of another seismic shift. Every experiment, from underground detectors to space telescopes, is a vote in this grand cosmic election, a chance to nudge history toward one vision of reality or another. And when the results finally come in, they won't just tell us what dark matter is. They'll reveal what the universe is and our place within it. You might think unlocking the secrets of dark matter requires a billion-dollar lab or a lifetime of advanced physics training. But here's the beautiful truth. Some of the most exciting discoveries start with everyday people sitting at their kitchen tables. Across the globe, volunteers are making real contributions to dark matter research through projects like Zooniverse, where anyone with an internet connection can sift through telescope data, flagging strange patterns or anomalies that even the most sophisticated algorithms might overlook. It's a modern-day treasure hunt, except instead of gold, these citizen scientists are searching for the faintest clues of the universe's hidden architecture. Take the case of Galaxy Zoo, one of Zooniverse's most successful initiatives. When astronomers needed help classifying millions of galaxies, a task too vast for any single research team, they turned to the public. Ordinary people, from students to retirees, began sorting through cosmic images, identifying oddities like peculiar galaxies with unusual shapes or unexpected brightness. Some of these volunteers spotted gravitational lenses, the telltale warping of light caused by dark matter's invisible grip, leading to published papers and new avenues of research. One Dutch schoolteacher, Hanny van Arkel, discovered a completely new type of astronomical object, now called Hanny's voorwerp, while casually classifying galaxies after dinner. Her story isn't an outlier. It's proof that curiosity and patience can crack open cosmic mysteries, no PhD required. But citizen science isn't just about spotting oddities. It's also shaping how we simulate dark matter's behavior. Projects like Cosmology at home harness idle computing power from volunteers' laptops and gaming rigs, creating a distributed supercomputer that runs thousands of dark matter simulations simultaneously. Each simulation tests a slightly different scenario. What if dark matter particles are heavier than we think? What if they interact weakly with each other? By crowdsourcing these calculations, researchers explore possibilities far beyond the limits of traditional supercomputers, accelerating the search for dark matter's true nature. What makes these collaborations so powerful is their diversity. A professional astronomer might spend years focused on a single question, while a citizen scientist brings fresh eyes, spotting connections or irregularities that experts, burdened by assumptions, could miss. It's the scientific equivalent of the wisdom of crowds, the idea that collective intuition often outpaces individual expertise. When thousands of people examine the same data, anomalies stand out like sore thumbs, and patterns emerge that no single perspective could reveal. This isn't just feel-good participation, it's a paradigm shift in how science gets done. Dark matter's elusiveness demands creativity, and sometimes the key lies not in fancier detectors, but in more eyes on the problem. From classifying galaxy collisions to tagging dark matter filaments in simulations, volunteers are filling gaps that machines and professionals alone can't bridge. The next breakthrough might come from a retiree in Tokyo, a high schooler in Buenos Aires, or a night shift worker in Oslo, because in the hunt for the universe's biggest mystery, every perspective matters. After all, dark matter doesn't care who finds it, it just waits to be seen. Imagine a spacecraft hurtling through the void between stars, its hull bathed in starlight, its engines pushing against the emptiness. But that emptiness isn't truly empty. Every cubic kilometer of space, no matter how remote, contains a faint scattering of dark matter. The idea that this invisible substance could one day become a resource or a hazard for interstellar travel isn't science fiction. It's a frontier of astrophysics that could redefine how we explore the cosmos. The numbers seem discouraging at first. In our solar system, dark matter's density is estimated to be vanishingly low, roughly a single particle per coffee mug-sized volume of space. That's a far cry from the dense halos surrounding galaxies, where dark matter's gravity dominates. But low density doesn't mean negligible impact. Some theoretical designs for future propulsion systems, like the hypothetical dark matter drive, suggest harvesting these sparse particles as fuel. The principle is audacious. If dark matter annihilates upon contact with ordinary matter, as some models predict, even trace amounts could release bursts of energy. Picture a spacecraft equipped with vast magnetic nets, sweeping up dark matter like a whale filtering plankton from the sea, converting it into thrust. Far-fetched, perhaps, but so was nuclear fission before the 20th century. Yet there's a flip side to this cosmic fuel source. If dark matter particles are more energetic than expected, zipping through space at relativistic speeds, they could pose an unexpected radiation threat. Unlike ordinary cosmic rays, which shields can block, dark matter's ghostly nature means it might pass effortlessly through spacecraft walls, depositing energy directly into sensitive equipment or even astronaut biology. Studies of high-altitude radiation on Earth have hinted at anomalous particles that don't match known physics. Could some of these be high-speed dark matter, a whisper of danger lurking in the void? Missions like the International Space Station already monitor radiation levels. Future deep space vessels might need dark matter dosimeters alongside their Geiger counters. The key to unlocking dark matter's role in space travel lies in mapping its distribution with unprecedented precision. Right now, our models assume a smooth, diffuse spread throughout the solar system. But what if there are clumps, microscopic clouds of dark matter drifting along gravitational contours, invisible whirlpools in the cosmic current? Spacecraft navigating near Jupiter's orbit, for instance, might encounter higher densities due to the planet's immense gravity well. Future probes equipped with dark matter sensors could chart these hidden currents, turning a theoretical mystery into a practical navigational tool. The same way sailors once used stars to guide their ships, interstellar travelers might one day ride dark matter's unseen tides. This isn't just about engineering challenges, it's a paradigm shift in how we view the universe. For centuries, space was the backdrop, the stage upon which exploration unfolded. But if dark matter is both a potential fuel and a navigational landmark, then space itself becomes an active participant in the journey. The silent architect of galaxies might one day whisper directions to our probes or power them toward destinations we've only dreamed of. And as we reach farther into the cosmos, we're not just passing through the dark, we're learning to speak its language. time isn't the constant we imagine. It bends, stretches, and warps under gravity's influence, a phenomenon Einstein revealed over a century ago. Near massive objects like black holes, clocks tick slower relative to those in empty space, as if gravity itself can pull time out of shape. But what if the universe's most abundant mass, a dark matter, is doing the same thing on a galactic scale? Picture a galaxy's invisible halo not just as a gravitational anchor, but as a subtle timekeeper, gently slowing clocks within its reach. The effect would be vanishingly small, but in a cosmos where precision is everything, even nanoseconds matter. Atomic clocks, humanity's most exact timekeepers, could be the key to detecting this hidden influence. These devices, accurate to within 1 second over billions of years, are sensitive enough to measure time's distortion caused by Earth's gravity, or even altitude changes as slight as a staircase. Now, researchers are asking, could they also sense dark matter's whisper-thin drag on spacetime? The math suggests yes. In regions where dark matter is densest, like the cores of galaxies or the intersections of cosmic filaments, time might lag by fractions of a second over millennia. That's not enough to notice in daily life, but for a network of synchronized atomic clocks spread across space, these discrepancies could paint a map of dark matter's hidden contours. The implications go far beyond curiosity. If dark matter warps time differently than ordinary matter, it could hint at something profound, that dark matter interacts with space-time in ways we don't yet understand. General relativity assumes all mass bends the fabric of the universe identically, but what if dark matter's grip is subtly distinct? Some theories propose that dark matter's particles, if they exist, might generate unique gravitational signatures like a shadowy fingerprint pressed into the flow of time itself. Detecting this would upend our models, revealing that gravity isn't just bent by mass but by the nature of mass. The wildest possibility, dark matter might not just influence time, it could be entangled with it. In quantum physics, particles can exist in multiple states until observed, a paradox called superposition. If dark matter shares quantum properties with the fabric of spacetime, its presence might create fleeting ripples in time's passage, like a stone skipping across a pond. Experiments are already underway to test this, using entangled atomic clocks to hunt for synchronized anomalies that could signal dark matter's passage. It's a long shot, but so was the idea of black holes before we photographed one. This isn't just about refining clocks or tweaking equations. It's about realizing that time, the most familiar yet mysterious dimension, might be a dialogue between the seen and the unseen. Every second that ticks is shaped not just by the stars and planets we know, but by the silent, gravitational hand of dark matter, a reminder that even time itself isn't beyond the reach of the cosmos's hidden architects. The cosmos has always been a muse, but dark matter, invisible, intangible, poses a unique challenge to artists. How do you paint what cannot be seen? The answer lies in the collision of data and imagination, where supercomputer simulations become brushstrokes and scientific models transform into sculptures. Take the work of artist Leah Halloran, whose cyanotype prints trace the delicate filaments of dark matter's cosmic web, translating gravitational maps into ethereal blue waves that seem to pulse with hidden energy. Or consider the immersive installations of Team Lab, where visitors walk through swirling galaxies rendered in light, their bodies disrupting projections of dark matter's gravitational pull like stones tossed into a pond. These creations aren't just beautiful, they're translations, turning the abstract language of astrophysics into visceral experiences. Science provides the raw material dark matter distributions from projects like the Millennium Simulation, which modeled the universe's growth over billions of years. But artists rework these datasets into something tactile. In the dark matter VR experience developed at the University of Sussex, users don headsets and glide through a galaxy's halo, their hands brushing against invisible particles represented as shimmering points of light. The effect is revelatory as suddenly the obscure concept of a dark matter halo isn't just a term in a paper, it's a place you've visited, a space you've touched. This fusion of art and science doesn't merely illustrate, it illuminates, revealing patterns and connections that equations alone might obscure. Even music has joined the conversation. Composer John Boswell's Symphonies of Science series incorporates sonified dark matter data, assigning pitches to particle densities so that clusters sing in chords and voids resonate with deep, hollow tones. The result is a haunting soundscape where the universe's hidden structure becomes audible, a chorus of gravity's unseen hand. Similarly, the Particle Shrine installation by Ralph Beaker uses kinetic sculptures to mimic dark matter's hypothetical interactions, their delicate movements choreographed by live feeds from particle detectors. Here, art doesn't just reflect science, it interrogates it, asking how we perceive evidence that defies our senses. The power of these collaborations lies in their ability to democratize wonder. Not everyone can pass a Fourier transform or interpret a redshift graph, but anyone can stand beneath a projection of the cosmic web and feel awe. When the Rubin Observatory releases its torrent of data, it won't just be astronomers mining for discoveries, artists will too, transforming numbers into narratives that resonate on a human scale. Dark matter's mystery endures, but through art, it becomes a shared journey rather than an academic abstraction. The universe's silent architect may never fully reveal itself, but in these creative acts, we find a new way to listen. Long before telescopes peered into the cosmic abyss, cultures wove stories of invisible forces shaping the world. The ancient Greeks spoke of the ether, a mysterious fifth element permeating the heavens. Hindu cosmology described an unseen akasha, the fabric underlying reality. Polynesian navigators charted their courses by the pull of mana, an intangible energy flowing through all things. These traditions, separated by oceans and millennia, share a common thread: the human instinct to explain the unseen. Today, dark matter carries that torch forward, a scientific mystery echoing our ancestors' spiritual awe. What's fascinating isn't just the parallel between myth and physics, it's how differently cultures interpret this resonance. For some theologians, dark matter's omnipresent yet elusive nature mirrors descriptions of the divine. Jesuit astronomer brother Guy Consolmagno has likened it to Thomas Aquinas's vision of God, not a thing among things but the ground of all being. In indigenous Australian traditions, where the dreaming exists as a timeless, invisible dimension shaping the land, cosmologists find poetic kinship with dark matter's hidden scaffolding. Even secular perspectives recognize the narrative power. Sci-fi author Lou Sixon reimagined dark matter as a shadow civilization in the three-body problem, blending science with ancestral fears of the unknown. Yet the contrast between ancient mysticism and modern empiricism is equally revealing. Where myth personified invisible forces as capricious gods or spirits, science seeks impersonal laws. The Yoruba people of West Africa once attributed cosmic order to the trickster god Eshu, who balanced chaos and creation. Dark matter, by comparison, operates without intent. Its gravity sculpts galaxies as blindly as wind carves dunes. This shift from agency to abstraction marks one of humanity's great intellectual journeys, replacing superstition with equations, yet retaining that primal wonder. The tension between these worldviews isn't just philosophical, it's practical. Some researchers now collaborate with indigenous knowledge keepers, comparing oral traditions about celestial patterns with dark matter's gravitational effects. In Chile, astronomers working near Atacama's telescopes consult with local Aymara elders, whose ancestors mapped the stars without lenses, seeking cross-cultural insights into the cosmos's hidden layers. These dialogues reveal a surprising truth. While science demands evidence and myth thrives on metaphor, both are languages for grappling with the ineffable. Perhaps the most profound connection lies in dark matter's challenge to human centrality. Just as Copernicus displaced Earth from the universe's center, dark matter dethrones visible matter as the cosmos's primary substance. Buddhist texts spoke of emptiness as the fundamental nature of reality, a concept that eerily anticipates modern cosmology's revelation that most of the universe is literally unseen. Whether framed as spiritual enlightenment or scientific discovery, the lesson humbles. What we perceive is but a fragment of what is. This intersection of belief and physics isn't about proving one right. It's about recognizing a shared lineage of curiosity. From shamans reading the sky to physicists decoding redshift data, we've always sought to name the invisible hands moving the heavens. Dark matter, in its elusive grandeur, becomes more than a particle or a force. It's the latest chapter in humanity's oldest story. And like all great myths, its meaning grows richer the more we learn how much we have yet to know. Quantum mechanics and dark matter might seem like strangers, one governing the bizarre behavior of particles too small to see, the other shaping galaxies too vast to fathom. Yet dig deeper and their connection becomes tantalizing. Take the action, a hypothetical particle born from quantum field theory's most elegant equations. Originally proposed to solve a puzzle about the strong nuclear force, actions have an unexpected side effect. If they exist, they could be dark matter. Think of them as cosmic chameleons, barely interacting with ordinary matter but pooling in vast, invisible halos around galaxies. Unlike the clunky WIMP favored by earlier theories, actions would be feather-light, trillions of times less massive than an electron, flickering in and out of existence like quantum fireflies. Their discovery wouldn't just solve the dark matter riddle, it would confirm that the subatomic world and the cosmic web are woven from the same strange threads. Then there's entanglement, quantum mechanics' most baffling phenomenon, where particles separated by light years remain mysteriously linked. Could dark matter play by these rules? Some theories suggest dark matter particles might form entangled pairs across galactic distances, their ghostly connections subtly influencing how galaxies cluster. Picture a universe where invisible threads of quantum correlation stretch between galaxies, as if the cosmos itself is whispering secrets through the dark. While this idea remains speculative, it hints at a profound possibility. That dark matter isn't just passive scaffolding, but an active participant in quantum weirdness on a cosmic scale. The real frontier lies in merging these quantum clues with cosmology's grand sweep. For decades, physics has struggled to reconcile the infinitesimal quantum mechanics with the immense general relativity. Dark matter could be the bridge. If it's a quantum particle like the action, its behavior might reveal how gravity operates at microscopic scales, a missing piece in the puzzle of quantum gravity. Alternatively, if dark matter interacts through undiscovered quantum forces, it could hint at a hidden sector of particles and fields, a shadow universe operating alongside our own. Experiments like the Action Dark Matter experiment ADMX are already tuning into these possibilities, using ultra-sensitive detectors to listen for actions converting into radio waves in strong magnetic fields. It's like scanning the cosmos for a station that's never broadcast before, unsure of the frequency but certain the signal is out there. What makes this search so thrilling is its potential to unify physics' greatest mysteries. Dark matter's quantum nature might explain why the universe has structure at all, why galaxies didn't simply dissolve into a featureless void. And if quantum entanglement extends to cosmic scales, it could redefine our understanding of space itself, not as a static backdrop, but as a dynamic network of invisible connections. The quantum cosmos isn't just a frontier, it's a mirror reflecting back the deep unity of a universe where the smallest and largest phenomena are far more intertwined than we ever imagined. Imagine a classroom where students aren't just reading about dark matter, they're holding it in their hands. Well, not literally, but close enough. Educators have crafted ingenious ways to make the invisible tangible, like using a simple salad spinner filled with marbles to simulate galaxy rotation. As the spinner whirls, the marbles cling to the edges, defying expectations just like stars in a dark matter-rich galaxy. It's a hands-on, aha moment that transforms abstract equations into something visceral. This kind of creative teaching isn't confined to science labs. Apps like Universe Sandbox let students tweak the amount of dark matter in a virtual galaxy and watch in real time as stars either spiral apart or stabilize, a digital playground for cosmic cause and effect. Meanwhile, museums are stepping up with immersive exhibits. The American Museum of Natural History's Dark Universe Planetarium show transports visitors into a 3D map of the cosmic web, where filaments of invisible matter glow like neon threads, revealing the hidden skeleton of the universe. YouTube has become a powerhouse for dark matter education, with creators like Veritasium and PBS Spacetime distilling complex theories into bite-sized, visually stunning explanations. Their secret analogies that stick. One viral video compared dark matter's gravitational pull to a hidden magnet under a table, subtly steering metal shavings, stars into patterns that hint at its presence. It's science storytelling at its best, using the familiar to unlock the extraordinary. But the most impactful tools might be the simplest. A high school in Norway built a low-cost cloud chamber to track cosmic rays, challenging students to spot particle trails that could theoretically include dark matter interactions. Though the odds are astronomically low, the lesson is profound. Science isn't just about answers, it's about the thrill of the hunt. By making dark matter accessible, educators aren't just teaching facts, they're cultivating curiosity. When a 10th grader graphs galactic rotation curves and sees the mismatch between prediction and reality, they're not just solving a problem, they're stepping into the same shoes as Vera Rubin, feeling the same electric doubt that sparks discovery. And that's how the next generation of cosmic detectives will emerge, not by memorizing textbooks, but by experiencing the mystery firsthand. Dark matter might seem like the ultimate abstract pursuit, a cosmic detective story with no obvious ties to our daily lives. But peel back the layers, and you'll find this elusive mystery is quietly fueling technological revolutions far beyond astronomy. Take those ultra-sensitive detectors buried deep underground, built to catch the faintest whisper of a dark matter particle. The same technology that shields them from cosmic noise is now revolutionizing medical imaging. Doctors use refined versions of these sensors to spot tumors earlier than ever, detecting subtle energy shifts in tissues that older machines would miss. It's not just about seeing deeper into space, it's about seeing deeper into the human body with clarity that saves lives. Then there's the computing power needed to simulate dark matter's cosmic web. Modeling how trillions of particles interact across billions of light years requires algorithms so advanced they push supercomputers to their limits. These simulations don't just help astrophysicists, they train AI systems to recognize complex patterns, from predicting weather disasters to optimizing supply chains. The machine learning techniques honed for dark matter maps are now used by financial institutions to detect fraud and by epidemiologists to track disease outbreaks. What began as a tool to understand the universe's structure is reshaping how we navigate chaos right here on Earth. Even the material science behind these experiments has spin-offs. To build detectors that won't trigger false signals, engineers pioneer ultra-pure metals and ceramics, materials now used in quantum computing and next-generation batteries. The quest to shield dark matter experiments from stray radioactivity led to innovations in radiation-resistant alloys, critical for nuclear waste storage and space exploration. Every technical hurdle overcome in the hunt for dark matter sends ripples through industries no one could have predicted. The economic argument for funding fundamental research has always been this: curiosity pays unexpected dividends. GPS satellites rely on Einstein's relativity corrections to function accurately. The Internet grew from a particle physics data sharing project. Dark matter's payoff might not be as immediate, but history shows that probing the deepest mysteries yields tools we didn't know we needed. When governments and private investors fund dark matter research, they're not just buying telescope time, they're seeding the technologies of tomorrow. The same labs searching for WIMP could incubate the next breakthrough in clean energy or nanotechnology, proving that the line between impractical wonder and world-changing innovation is thinner than we think. Critics argue the costs are too high for uncertain returns, but they miss the bigger picture. Dark matter research is a catalyst, forcing us to invent solutions to problems we wouldn't encounter otherwise. The struggle to communicate data across global collaborations birthed faster fiber optic networks. The need to process exabytes of cosmic observations accelerated cloud computing. This isn't just about finding a particle, it's about building the intellectual infrastructure to handle discoveries we can't yet imagine. The real ROI isn't in dark matter itself, but in the technological ecosystem it forces us to create. So the next time someone asks why we're spending billions to chase invisible matter, the answer isn't just about galaxies or gravity. It's about how the tools we forge in this quest, the sensors, the software, the systems, are already rewriting the playbook for medicine, computing, and engineering. Dark matter might hide in the shadows, but its impact on our world is stepping into the light. Dark matter doesn't care about passports or political divides. It blankets the universe indiscriminately, and so does the quest to understand it. Take the Large Hadron Collider, a marvel of engineering straddling the French-Swiss border, where physicists from over 100 countries collaborate in real time. This 17-mile-long ring isn't just a particle accelerator. It's a diplomatic achievement, a place where researchers from geopolitical rivals like India and Pakistan or the US and Iran work shoulder to shoulder, united by a shared obsession with the cosmos's secrets. The LHC's greatest output might not be Higgs bosons or supersymmetry data, but something far rarer, proof that humanity can prioritize curiosity over conflict when the stakes are universal. This spirit of collaboration extends beyond Geneva. In the Chilean Andes, the Vera Rubin Observatory rises like a scientific beacon, funded by institutions from the US, Chile, South Korea, and beyond. Its lens will capture the sky's faintest whispers, but its true power lies in its data pipeline, a torrent of cosmic observations instantly shared with researchers from Lagos to Oslo. No single nation could afford this project alone, nor could any single mind decode its revelations. The Rubin's design embodies a radical truth: dark matter's puzzle is too vast for silos. Even in the icy depths of Antarctica, international teams converge. At the South Pole, the Ice Cube Neutrino Observatory, a collaboration between the US, Germany, Sweden, and others, buried sensors deep in glacial ice to hunt for dark matter's indirect signals. The logistics alone are staggering. Swedish engineers designed the drill, American physicists built the sensors, and Belgian glaciologists ensured the ice itself wouldn't distort the data. This isn't just teamwork, it's a high-stakes relay race where the baton passes across continents, languages, and time zones, the unspoken rule of these projects. Credit flows where discovery leads, not where funding originates. When the Event Horizon Telescope captured the first black hole image, the authorship list read like a UN roll call from Taiwanese algorithm experts to Mexican radio astronomers. Dark matter research follows the same ethos. Papers from the Dark Energy Survey routinely feature 200 co-authors from 30 institutions, a testament to the humility required to tackle the universe's biggest questions. Ego dissolves at the scale of galactic halos. What's often overlooked is how these collaborations democratize science. Smaller nations without billion-dollar budgets contribute niche expertise. Brazilian programmers optimize simulation code, Kenyan engineers refine telescope components, and Thai universities host global data archives. The result isn't just progress, it's empowerment. A graduate student in Johannesburg can access the same datasets as a professor at Caltech, leveling the playing field in a discipline where answers hide in plain sight, waiting for fresh eyes. This model isn't without friction. Cultural differences in research styles, funding disparities, and even time zone headaches can slow progress. Yet the alternatives, nationalized space races or proprietary data hoarding, have proven less effective. Dark matter's enigma is a mirror. It reflects back our best collective instincts when we choose cooperation over competition. The next breakthrough might come from a Zoom call between Tokyo and Cape Town, or a shared spreadsheet updated by researchers in Buenos Aires and Helsinki. In a fractured world, these collaborations are more than science, they're a rehearsal for the kind of unity humanity will need to survive its next chapter, whether that's climate crises or interstellar voyages. The silent architect of the cosmos might just be teaching us how to build something equally profound, a shared future. The universe should be teeming with life, or so the Fermi paradox insists. With billions of galaxies, each hosting billions of stars, why haven't we found a single trace of alien civilizations? One tantalizing possibility lurks in the shadows: dark matter. This invisible substance doesn't just sculpt galaxies, it might be silently shaping the very conditions for life, or even hiding other civilizations from view. Consider planet formation, the delicate ballet of dust and gas that births worlds. Dark matter's gravity could subtly alter this dance, nudging debris into orbits that make rocky, life-friendly planets more or less likely. In regions where dark matter is denser, its pull might disrupt protoplanetary disks, scattering the raw materials for Earth-like worlds before they can fully form. Conversely, in the sparse outskirts of galaxies, where dark matter's grip is lighter, planetary systems could evolve undisturbed, their potential civilizations isolated by vast, empty stretches. The Goldilocks zone for life might not just be about a star's heat. It could be about the unseen density of dark matter in a given neighborhood. Then there's the shielding hypothesis. If dark matter interacts weakly with ordinary matter, could it also absorb or deflect signals that advanced civilizations might broadcast? Imagine a galaxy cloaked in a thick halo of dark matter, its radio waves dampened like a voice muffled under layers of fog. Even if intelligent life thrived there, their transmissions might never reach us, lost in the cosmic static of invisible particles. This wouldn't just explain the silence, it would imply that the universe's loudest, most detectable civilizations could be the outliers, the ones lucky enough to evolve in dark matter-poor pockets where their signals escape. But the wildest theory, dark matter itself could be the cradle of life or its executioner. Some models suggest dark matter particles, if they occasionally collide with ordinary atoms, might trigger mutations in DNA over geological timescales. On one hand, this could accelerate evolution, sparking complexity faster than expected. On the other, it might sterilize planets with lethal radiation, leaving galaxies littered with dead worlds. The difference between a life-bearing paradise and a barren rock could come down to the local dark matter weather. Of course, these ideas are speculative, bordering on science fiction. Yet they highlight a profound truth. Dark matter isn't just a player in cosmic structure, it's a potential game changer in the search for life. The same force that holds galaxies together might also be pulling the strings behind the universe's eerie silence. As we scan the stars for signs of others, we're not just looking for aliens. We're asking whether the universe's hidden architecture has been quietly shaping the story of life all along, and if so, whether we're the exception or just another whisper lost in the dark. Our journey through the shadowy realm of dark matter reveals a universe far richer and more mysterious than we once imagined. Think about it: every galaxy, every sweeping cosmic filament, every distorted beam of light we observe is just the visible tip of an iceberg, with the true substance of the cosmos lurking unseen beneath the surface. Dark matter isn't some abstract concept confined to textbooks. It's the unseen sculptor of the universe, shaping everything from the grandest galactic clusters to the delicate dance of stars within them. The very fact that we've deduced its existence not by seeing it, but by reading the subtle clues it leaves behind, is a testament to human ingenuity. Consider the ingenuity behind the hunt itself. We've turned the cosmos into a laboratory, using gravitational lensing as our microscope, galactic rotations as our scales, and particle colliders as our crucibles. Every null result, every baffling anomaly, even every dead end has been a step forward, narrowing the possibilities like a cosmic game of 20 questions. And the questions keep getting more profound. Is dark matter a single particle or an entire hidden ecosystem? Does it interact with forces we've yet to discover? Could it be the key to unlocking dimensions beyond our own? What's truly exhilarating is how far we've come with so little. Without ever touching dark matter directly, we've mapped its distribution across billions of light years, traced its role in the universe's infancy, and even guessed at its potential connections to black holes and quantum physics. The fact that we're grappling with these questions at all, that we've peeled back the curtain just enough to glimpse the universe's hidden machinery, is nothing short of revolutionary. The next chapter of this story is being written right now in underground labs, space telescopes, and supercomputer simulations, with tools like the Vera Rubin Observatory set to scan the sky with unprecedented precision, and next-generation detectors pushing the limits of sensitivity. We're closer than ever to a breakthrough. But here's the beautiful part: you don't need a PhD to be part of this quest. Citizen science projects, open data, and even the algorithms powering your social media feed are all playing a role. The hunt for dark matter is a collective human endeavor, a reminder that curiosity transcends borders and backgrounds. So as we stand on the precipice of discovery, let's not forget the bigger picture. Unraveling dark matter isn't just about filling in a gap in our equations, it's about rewriting our understanding of reality itself. Whether it's a particle, a shadow from another dimension, or something beyond our current imagination, the answer will redefine our place in the cosmos. The universe has kept this secret for 13 billion years, but the trail is getting warmer, and one day, perhaps sooner than we think, the silent architects will finally step into the light. What do you think dark matter is? A cosmic ghost, a multidimensional echo, or something stranger? Drop your theories in the comments, because in this grand puzzle, every perspective matters. And if you've enjoyed this journey through the invisible universe, don't forget to like, subscribe, and hit that notification bell. The next revelation could be just around the corner, and you won't want to miss it. Until then, keep looking up and keep wondering about the